Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about EV battery technology and its future promise. So let's dive deep into it. So what exactly is the problem? Well, we know exactly how much energy we should be able to get per kilogram of material. We know the density, we know the electron conduction, we know almost everything about it. So we know how much each chemistry should offer in terms of energy and in terms of power. Now, energy and power are two separate and independent category. Think in this way. Power simply means how big the generator is, and energy simply means how big the fuel tank is. So you could have like a ginormous generator that is like, 1 megawatt, but fuel tank is like barely, bro, I can only run it for 5 minutes. Or you could have something opposite where it's like, it's a tiny generator, but you have a tanker of fuel. So it's like, you start it and you forget about it. So these two variables are that we have to control for. So chemistry gives us like, some gives us very good power but poor energy, some gives us very good energy but very poor power, some are in balance. So generally that's what we have to figure it out. And right now as we speak, we know the chemistry, we got this, but chemistry says you should be here and we are getting here, the cars are here. What the hell, what is happening here? And again, it's not like a combustion engine. Electrical battery should be very efficient. So why the heck our batteries are huge, like hundreds of kilogram or sometimes almost a ton, but actual capacity, which again we calculated, should be like here and we are barely getting here. So it's like, what the hell happened? So right now we know on paper we have a lot of potential, but we are not getting that in real life. Like think in this way, nickel metal batteries were utilized in 1997 and 1998 in Toyota hybrids, and then we jumped to lithium ion. So you're like, okay, problem solved? Not really. So it's one of those things. Chemistry is not the bottleneck as people think it is. And if you right now look into the budgets of almost all EV manufacturers, big ones specifically, where their money is being sunk, most of them are sinking the money in the battery itself, nothing else. Just like how the heck you get the on theoretical power and your real power. Like basically everybody is here, you want to make sure that you are here. So that's where money is going right now. So R&D budget. So if you're like, hey, I'm opening an EV company, the amount of money you will sink into the drivetrain would be minimal in compared to the battery technology. So, and everything matters, not just the cell. It's not like, oh, what if I had a better cell supplier? Yeah, it would help. It's not a bad thing, but that's just one variable. And we know the chemistry. We good. Like we can tell you, like if you have capacitor, you get this sort of power and you can get this sort of capacity. So we know this. Like we know how lead acid works, how lithium ion works, how nickel cadmium battery works and all that. We good. We got this. We good. We have been making this. It's just that it's not, packaging is not good. So there is a genuine problem here. So the first solution, that the first tool humanity deployed, was prismatic cell. Prismatic simply means a square boxy shape of rigid material. What is this material made out of? There are a lot of options. It could be made out of some sort of glass fiber. It could be made out of aluminum. It could be made out of steel. Steels are generally not used for EV application. They are generally used for static application. But you could use it if the cost is not an issue and you do not need a lot of power to weight ratio. Okay, something rigid that handles the jelly roll. What is the jelly roll? It's a technical quote-unquote manufacturing term, which simply means the anode, the cathode, the separator, the electrolytes, all of that. That basically stuff that goes inside it, basically the powder part. So that electrolyte is the thing that gives you the energy, and everything else is not desirable. You do not want anything else other than that. So that's what we are trying to optimize. So in the early days, we used to have tab prismatic cells. So basically prismatic had giant rolls, and then at the one end of anode we had one conductor, and the other end of cathode we had another. So it was like, it was utilizing all of the area. While this does allow very low cost construction, it does allow a lot of capacity, as in your kilowatt hour was awesome. Your kilowatt was very poor, as in how much oomph you can drain out of it, because there were tiny tabs. You were like, nah. So it was more of like, backup kind of system. So you have a big ass battery and you're like trying to back up a small laptop for 50 days. You could do that. It was super awesome for solar and all that is good. But then you're like, okay, what if I put in an electric vehicle and I need high C rating, 10C, 20C? Those things are like, bro, I will melt. Flat out. It's like, bro, I can't do that. So fundamentally, we had to switch to tab design to tabless design. And yes, tabless design came long into prismatic before Elon Musk made it quote-unquote popular. So it was there. And again, all you do is take this, offset it, and fold everything on one end, and then laser weld it. So tabless. Now tabless is preferred because again it allows you to have much better thermal conduction, because again you do the jelly roll is the one that is getting hot or cold. So you want to leach energy away from it, especially when you are draining a lot of power or dumping a lot of power, charging or discharging. And that sort of time, the energy, the thermal energy has to conduct through it. So the most efficient part is the big ass conductor that you have for the current. In tabless design, that becomes so huge that it can actually wick heat away from the inside of the jerry roll from the to the outside casing very efficiently. So thermal and electrical properties improve. Not only just the thermal, electrical also. So instead of same amount of jerry roll, basically let's say 1 kilogram of jerry roll was used, exact same chemistry. Just by changing the geometry from tab to tabless, you can go from the cell can barely do 2C to 20C of discharge. And it's like, I got this. The internal cell resistance goes down drastically, cell lifespan improves drastically, especially in high load scenario. So we go to generally tabless now. There is one problem with tabless design is that because you are offsetting the anode and cathode to fold them, it generally prefers to have anode and cathode coming on the other ends. So it does generally have to have basically anode and cathode coming on the other ends. Now let that be very clear. It's not necessary. There is no law of physics. You cannot contain it itself. It's just not done. Most of the time, most of the cell I have seen generally have anode and cathode coming on the other ends. So you generally get opposite terminals, opposite polarity also. Now it has one of the best electrolyte to packaging ratio. That's why it is utilized by every single cell manufacturer, EV manufacturer right now. So if you remove Tesla, most of them will use this. Like there is no second best or third. No, most of them are using this, right? Because again, the powder, the jerry roll to actual casing ratio is one of the best. You can have like a very light packaging and very heavy jerry roll percentage. So people love this. And it does require compression. That is another penalty of it. Once you fold it, jerry roll, if it's not compressed well enough, it could develop a void and it would cause cascade failure. So your battery could go poof. So for that reason, it has to be compressed. You cannot compress too much of it because again, that could damage it and again, kaput. So in those sort of scenario, you can understand why it requires so much R&D. Like not only you have to have the package, you have to package it, like physically, and it cannot loosen. Let that be very clear. It cannot loosen. Oh, like I've been using it for 10 years and it became loose. No, it has to maintain that exact same PSI. So it's very tedious. And again, that's why for many of the static application, they choose steel case. So the case itself provides enough oomph that they are like, we do not need to compress it externally. So you have to spend a lot of R&D. Now, benefit is that if you actually do that, you get a lot of kilowatt hour, you get a lot of kilowatts, and you also get a lot of weight saving, meaning how much your final battery box would be compared to how much kilowatt hour it has. It would be really good. So everybody learn, but it does need a lot of R&D. Like you can look into Monroe Life where they are tearing down all the battery banks, and you can easily see like how some of them have like so much bus bar. It's like, bro, half of your vehicle box is just bus bars, electrical and all that. Others have like such a poor thermal systems where it's like, bro, what the hell were you thinking? Like Nissan's first generation where they're like, battery can handle it. And then 5 years later, it's like, yeah, we have to do recall on them. So fundamentally, it does require good R&D to utilize it properly. And most systems, this is the most commonly used system in EV industry right now. Then we come to the Elon Musk baby, which is 4680. Now, Tesla is one of the major manufacturers that are utilizing cylindrical cell rather than prismatic cell. Now, the reason for that is cylindrical cells are inherently, geometry-wise, stronger. Because again, it's a cylinder. Even if you have the same millimeter thickness in terms of your casing in prismatic cell versus cylindrical cell will be like, I'm geometry-wise much better. So you do not require external compression. That is one of the very core advantage. You do not have to spend millions of dollars. Like how the heck we compress it and it remains same at every temperature versus don't worry about it. So cylindrical cell does give you that benefit where it's like, don't worry about it. So it does give you that. You do not need mechanical compression. That's the good part. But you can understand if you have cylindricals, it does not have good fill efficiency, meaning not only your electrolytes to case ratio would be poor, your whole battery box would be poor. It will be filled with voids that again, and you cannot do anything. It's exactly like how electric motors are trying to balance between round copper round wires to hairpin stators, because again, hairpins allow you to have more copper. Same thing here. In there we want copper, here we want electrolyte fill ratio is not good in this. So what can you do? Let's say you agree to like you're going to use cylindrical. What is the next best tool, next best balancing lever you have? Well, first thing is you increase the cell size. That's the easiest lever you can pull. So you can go from 18650. So this is the phone that Elon Musk did to Panasonic in 2008. Is like, brah, you got a lot of laptop cells. Like Panasonic is like, yeah, bro, we got this, we're good. So it's like, what if you give me a few thousand of this? It's like, what the hell are you gonna do? Don't worry about it. I'm gonna dunk them in oil and I'm gonna cool the hell out of it. And then I'm gonna run power through it. So that's how they built the first routes, and that's why people are like, wait a minute, you're telling me that electric vehicle can actually be good? Yeah. So 18650, it's good. It got Elon Musk its footing, the early money and all that. Then he spent that money to get a better cell that was 2170, bit bigger. So better electrolyte to cell ratio. And then finally Elon Musk crossed, I think $1 trillion. And that point is like, okay, now we can pull out some serious money. At that point in time, they upgraded it to 4680, this puppy. So 46 millimeter is the diameter and 80 millimeter is the length. So it's a big puppy. Like, I do not think you want a cylindrical cell that is bigger than this. This is like, I think, the best they can do. Again, because again, you can make it bigger, but where will you put it in your car? So they made it as big as they can make it. And jerry roll, again, tabless design. Now tabless in Prismatic is super easy to do. Here it's kind of difficult, but they figured it out the same thing. Yeah, slice it, basically the roll is being made and you slice it. So rotary blade keeps slicing it and then you keep folding it. Then you laser weld the hell out of it. Then you laser weld that thing into the casing. So this is another benefit of cylindrical cells. They are generally structurally sound enough where you can utilize it as a cathode. So they laser welded. These black lines are laser welding. So that becomes the cathode. And top side, they have a plastic insulator and aluminum laser welded to a plate. Plate is laser welded to a current collector on the positive end. Now that's how they got the tabless design. Now be mindful, I have provided amazing teardown videos of the actual cells, and not only Mark 1 cells, Mark 2 cells also. So that's there, and it's very good in terms of thermal capacity. It's very good in terms of electrical, because again, you can understand, if copper side wants to dump heat, it can just like, bro, I'm connected so much, there is no like thermal paste. It's like I'm metal to metal connected. I'm welded to this puppy. I'm gonna dump all the energy. So it's a really good structure in that regard. And electrically, same thing. All the electrons can be like, I got you, fam. I got you. This puppies can handle 20 C without any 2 issues. Like, bro, I got this. I got this. I'm good. So that's the good part. That's why they can actually have only few strings of these cells and they're like, bro, we good. They do not need like, multiple cells in parallel in order to give you the oomph. It's like few of these is like, bro, I got this. Me good. And it can sustain it, because again, internal resistance is low enough. It does not heat up when you're like, I'm drawing the power. It does not heat up. So fundamentally, so jerry roll is welded on both ends, and they also have figured it out that because again, they are using spicy chemistry which can become a rocket. So they're like, okay, let's give it a nozzle. So this ball bearing is the ejection nozzle, where if the jerry roll goes kaboom, so it's gonna go. Now assume the ball works out, everything is fine, it's a small nozzle, it will punch a hole in the car, and it's designed in such a way that it will punch hole downwards. And reason is that you do not want the chassis, basically occupant should not be harmed, so it's going to punch a hole downwards. Another aspect is, if it punches a hole in the bottom, firefighters can inject water through there, so that's why they want it. And another is, there is another laser weakening in the other end of it. So let's say this ball bearing failed, you put epoxy there and it failed, no problem, it's going to boom the whole bottom out. So it's going to become a rocket. When something bad happens, it will become a rocket. You cannot stop it. They just double sealed it, where it's like, okay, one nozzle and the second whole nozzle is there. So it does work. However, let that be very clear, this tabless design, I do not know what is the patent situation on this, but this is available by other manufacturers also, and they are in use. It's not like, oh, in future it will be available. You can just buy Bosch batteries that have that. You can buy Milwaukee drill batteries that say it's a tabless battery, and you can X-ray it. Is exactly the same thing, although it's not in the same size. 4680 is not the same size. Those are generally in 2170. I've not seen tabless in 18650. If you have seen it, please link down below, but most of them I have seen in drill batteries, they are 2170. So that's available right now. Other OEMs can do that. And what about cooling? Well, most of the cooling is done by the side wall. That's where they have the most amount of contact. Again, actual energy is coming through this tabs. Tabs are dumping energy from the actual spice. It's dumping the energy into the conductor. Conductor is dumping into the cell wall. Cell wall is dumping the energy into the coolant. They have the serpentine coolant and going next to it. So that's how they're getting the cooling from cylindrical wall. Now, vents are there, everything is there. Now, another benefit of, because they are using cylindrical cell, it does have one benefit, that it can act rather than a fragile baby that you have to baby and it's like, no, you have to compress it precisely, and this, it does act like a structure where it's like, I got you, fam. So that is one another advantage, where it's like, no, I got you, fam. So this is 4680, Elon Musk's baby right now. Then we come to another spicy topic, that is blade battery. Now, blade battery is basically somebody looked at prismatic cell and is like, okay, this is not gonna cut it. They brought their engineers, they brought their cell chemists, they brought their manufacturing engineers, they brought their BMS engineer, got everybody in the room, and this was BYD. Because again, BYD had the scale, same as Elon Musk had the scale to order giant things. They had the scale to design their own battery. So they took the prismatic system and they're like, okay, everybody in the room, tell us what do you want. Everything about this battery is not, whoa, it's, huh, that's clever. That's clever. Everything about this battery chemistry is like, huh, that's smart. So let's start. First, tabless design. Duh, you need a lot of oomph for electric vehicles, so tabless design. And terminals are on each ends. Now, they're very clever with that. If you have terminals on each end, you're going to have wiring on both sides. But if you do it cleverly, you need to weld, right? You need to do a lot of laser welding. So they have offsetted. So it's not a basically symmetric. So it's offset like this. So it's like tuk, 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 tuk. So basically you have a AA battery, how you used to do in, electric toys. It's like A, then you flip it, flip it, flip it, flip it. Exact same thing they are doing. And because they have spent time with engineers who have to actually weld the damn thing, they're like, hey, what would make your life easier? It's like, hey, wouldn't it be nice if it was offset? And it's like, we can work with that. We can offset it. Ta-da, laser tabs. They can just mass produce this tab and just like, done. On top of that, they're like, hey, what about battery management system? Because again, trust me when I say this, it's complex AF. And if you have like 600 cells, 800 cells, God help you if you have that many cells in series, the BMS becomes brutally painful to manage. And sometimes you have to have hybrid BMS where you have module BMS that is managing inside it, and then you have a master BMS that is managing each of the modules. So it's idiotically power. Not only you have high voltage wires, you have this low voltage, low power wires, so to say, and it is painful, very expensive. They're like, hey, we have this many conductor and it's almost acting like a very good structure. What if we put the PCB on it? Ta-da! This literally looks like somebody sat down. It's like, hey, what would make your life easier? It's like, bro, we have the PCB, right? What if the PCB was directly mounted on the battery? It's like, huh, let's mount it. Done. Go home. They barely need 2 to 3 wires to talk from side A to side B. Done. Go home, sweet dreams. And maybe not even that. They're like, we good, bro. We good. So BMS is also good. Now, what about this long shape? Well, this is where things get interesting. They are improving the basically surface area to volume ratio. Because you want the heat to go away. If it's a giant tank and lot of electrolyte, it's a really bad idea. It's almost like an insulator just by the surface area to volume ratio. But if you make it thin and long, it becomes very efficient in terms of surface area. So electrolyte has a lot of surface area to radiate heat away. And if you can have any conductor plate that is leaching heat away, it's just like, I got you, I got you. So that also makes it very easy to cool. And how do they cool it? They run a air conditioning plate on top of. And I'm like, why they do that? Because again, I've seen other design where they have a cell has a metal plate. Again, cell is in a pouch. They have an aluminum plate that is thermally bounded to that, and then they've folded the plate. Then you have giant layer of like almost 5 millimeter thick layer of what you call thermal compound. Then it's going connecting to a liquid heat exchanger. They're like, ain't nobody got time for that. It's not manufacturable. So it's like they just put everything on flat and bam, again they do put thermal glue there, and they put a AC condenser evaporator plate on it directly. So another benefit, it does have epoxy layer and all that. So heat will take time to go away. So what can you do? Well, you can increase the temperature delta. If you increase the temperature delta, heat will go away willingly. So not only you improve the cell's ability to dump heat, you also improve how you are putting it into car. So ta-da! So it's very efficient. And again, another aspect is they reduce the numbers of quote-unquote module. This breakdown from Monroe Live, I've linked the novel. It only has 2 stacks. While you look at we have 4 stacks or 8 stacks or 16 stacks. It's like, no, ain't nobody got time for that. And this is a fatter battery. There are even slimmer battery with just like 1 line. Ain't nobody got time for that. Just like 1 line. Now, is there a penalty to that? Yes, if one cell poops the bed, it poops the bed. Your car poops the bed. So even, I'm not talking like in terms of like something catching on fire or things of that nature. It's just that even one cell has a failure rate. Basically, they have to trust their own internal QC. Otherwise, this is like playing with fire. And to make sure that, because again, they want to make millions of that, they cannot afford even few of them catching on fire. Even though statistically it would be a very insignificant, it will have very serious reputational damage. So they are like, hey, what if we do not play with fire? and we just put lithium iron phosphate. Now you're like, does not that mean it's going to give you a very lower kilowatt hour? While it can give you the kilowatts power wise, it does not have energy. They're like, no, this package wise, like the actual package is very energy dense. Why? Because they improved the packaging. They made sure that you do not have super heavy bus bar. They made sure the BMS does not have like freaking 5 kilograms of wiring. They made sure everything is cheap and easy to assemble. So the final package, the thing that goes into your car, is far more efficient. So that's why, like, this thing literally looks like somebody sat down, is like, let's design what we need. So everything is good about that, and it's self fine-tuning to cooling power, everything, packaging, BMS, manufacturability, everything is just efficient. So blade battery makes sense in terms of, like, basically this is what happens when a team works collaboratively. It's like, hey, what do we need? Everybody works together. Because that's a tiny thing. Like, hey, what if we offset it? It's like, no, it's a huge thing that simply makes your life easier. BMS becomes an easy thing. These are things that means somebody was actually paying attention. What do you need? What do you need? What do you need? So I'm happy that this is a good engineering. Me happy. Then we come to understand what can we expect in the future. Well, we have settled on lithium iron phosphate as of now by bypassing Tesla almost, and again that's why they have missile valves inside the system. It's okay. Basically, can it catch on fire? It can burn. It can burn. If the chemistry is done correctly, it will burn like a wood or something like that. But it should not be like fire. It should not be like that. So, and what about the chemistry change? What if we add silicon? What if we add that? Trust me when I say this, even if we change it, it would be subtle at best. Now, again, the certain impacts could be significant, like a cycle life. That's where everybody is pouring their money in right now. We want the batteries to last 20 years or 30 years. So cycle life, you can see a lot of difference, but do not expect like, okay, back in the day, battery used to be like, 10 kilowatt hour. Now I'm getting 30. Yeah. If that level of change is happening, that means somebody is fixing the packaging rather than cell chemistry. So all other factors need to be optimized. Basically, how quickly you cool the battery, how quickly you heat the battery. All of those plays a much bigger role than you realize. For example, thermal management not only requires cooling the cell, it also requires heating the cell. Specifically in winter month, when the temperature can drop, you do not want to start charging it if the cell temperature is below 20 degrees Celsius. They like to be 20 to 30 degrees Celsius. So you have to heat it up very quickly. So that has to be very seriously accounted for. Like, this is another design that I'm seeing, Z folding. Basically, if you look into jerry rolls or big canister cells, issue is that if you keep rolling it, you realize that you have a giant wasted space. So how do you reduce it? Well, you roll it twice. So, but you can see that like it's fundamentally wasteful. What is the next best? Well, Z folding. That way you can stack a very thick, double C kind of thick. You can have thick cell, and with tabless design you will not have the issue of like how the thermal conduction will work and all that. So that could really improve prismatic cell to next level, where you can have ginormous prismatic cell for buses and trucks and all that. So that is another option. Another is like, what if you want cylindrical cell? So what can we do? Well, cylinders does not allow you to have good packaging. So they're like, okay, what if we do not worry about packaging? What if we put liquid immersion? So you have a long cylindrical cell and you seal it from a back end and bottom end, and then you run dielectric directly through it. Basically, you run oil through it. And what is the benefit? Well, you can maintain the temperature to 2 degree plus and minus in very quickly. And as in, like, the hottest cell versus the coolest cell will only be delta of 2 degrees Celsius, which is good. And in terms of temperature swings, you can manage. Of course, assuming your air condition can handle it, you should be able to maintain a very tight tolerance. That simply means even if your chemistry is not amazing, you can outlast most people. So they are specifically focused on high load application like tractors, commercial city vehicles, and motor sports, those sort of thing. I've seen at least 2-3 companies working on that. So there are a lot of scopes left, but be very mindful. Sometimes we get focused on what if we add silicon. It's like, dude, we know what happens if we add silicon. We've known this from 1920. We have like, I think patents is like what, 1998. Patents is also ancient. It's just that battery starts to breathe. It's like, oh, what if we add silicon? It absorbs so much. Awesome. It just starts to it breathes. Like, your dielectric will fall apart instantaneously. Again, that's why we only add a little bit of it. So we know this, like everything in chemistry is like, whole periodic table is tested. So this is the future part. Packaging is the missing link, so to say. So this was my presentation on basically what the hell is going on with the battery market. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.